Hello, everyone. I am Steve Loughran. I work at Hortonworks on last year and a half cloud connectors, especially S3A. I'm going to give an update on the state of the world on all of them. Hopefully, I'll be giving demos. There haven't been enough demos this week, so live demos, genuine stack traces, all those going wrong. Who wants to see demos? Who wants to see demos go wrong? That was a mistake. Okay, keep your hands up. I like to get some audience participation here. I like to pick on somebody in the audience. Niels has volunteered, which is good for the rest of you. I pick on him because I know he's not important. Let's begin. This is me. I break things. Hands up who's using S3A connector. OK, I broke your code. Hands up who's using WASB connectors, Azure storage. I haven't broken your code, but I did break the HD Insights nightly build once. They weren't happy. Microsoft allowed to file bug reports directly against us, and they were not happy that day. Azure Data Lake, ADL, anyone? Google Cloud Storage. Google Cloud Storage? Nothing to do with me at all. But we do complain when their code's broken. We talk to them. Oh, and Amazon EMR and their connectors. Chris. So he's my colleague that worked on this code too. I have no idea what goes wrong with Amazon EMR. Sometimes we get bug reports in the Apache Juras, and we just say, tough. I'm giving some demos, Spark, REPL. This has all been done in Spark command line. Here is the preamble. I'm using, if you ever come across me, there's a large CSV file, 450 megabyte CSV file on Amazon. We use it for most of our testing for the Hadoop open source bits because Amazon pay all the I/O charges, and it's a big file to practice seeking around and downloading and things. It is CSV, but there we go. So as a preamble to demo, I've grabbed this CSV file. I've downloaded it locally to my laptop, which is doing all the work. And I've pre-prepared a schema for it as well. In Spark, you can just say scan through a CSV file to work out, infer the schema. And people say, oh, infer schema equals true. That'll scan through a CSV file twice. So a 450 megabyte file is very expensive. So do it once, and then remember the values. So I'm grabbing the file. Right at the bottom, I'm filtering it. I'm sampling 1% of it. And then I'm just saying, give me the subset where cloud covers 0, and just for 2014, which I cache. So I'm going to run through the file systems very quickly, see where they've been changing. Azure WASB is Azure's file system. It is a blob store, but it behaves roughly as a file system in terms of what we want. You can read data. You can write data. You can even do bulk deletes and renames. That's nice. They're usually very fast, apart from sometimes they stop for no apparent reason. I think there's some kind of garbage collection going on or something. It's shipping, and it's stable. They've done some work recently actually making Parquet and Awk.io better by just improving the seek algorithm. And they've done more work on Ranger. Who was in the previous talk? Previous talk, the Databricks one? The Microsoft talk, they discussed Ranger integration with WASB. It's there, however, it is all done client-side, meaning provided you've got a lockdown client running Hive queries, running SQL, that's fine. If you are instead actually running proprietary code in there, then it's not fine, as you can bypass it. Anyway, let us go with our first demo. I've got that data here. I'm going to upload it from locally to WASB. So I first copy my data, delete the existing copy, and then I do an upload. And I paste it into Spark shell. First stack trace. I suddenly realized I rebuilt this shell maybe and haven't actually initialized it. What was the error? Filtered CSV. Let's go from here and see if this works. Short pause here. I do actually really like the Spark shell for testing and experimenting stuff. Here we go. Because you can play with things quite nicely and get stack traces more easily. That was a classic stack trace. So now I'm going to upload data. This is me doing an upload. We're writing some Spark data back as ORC. It's taking that CSV file, it's actually parsing it. It is now doing the uploads. It's churning away. If you have a look closely at the output of what's going on, which is taking its time because it's remote, what's happening here is the pass will say ORC data / temporary something or other. What's happening there is the way Spark and MapReduce write their work to deal with failures and speculative execution is they write their data to a temporary directory. When a task finishes, that gets copied to a temporary directory for the job, and that's up to the Spark driver or the MapReduce app master. And then when the entire job commits, then all those files get renamed into place. We do that for failure handling. So there we can see it happening there. We did the upload. It took 40 million nanoseconds. So what's that? Or more than that. It took 40 seconds. So that's us copying up to WASB. If you're using, normally basically your choice of object store is driven by your choice of cloud provider. WASB is interesting. Well, Azure is interesting. You now have two options. And it's interesting to know why. I think if you want to know the answer to that, go to the Microsoft booth tomorrow, or this afternoon actually, and just say why is difference. ADL is new. It's actually built on Hadoop itself using Yarn. It has stronger security, and that the ACLs are actually done behind the scenes in the file system itself, so you don't have that vulnerability. And it uses OAuth to authenticate. The other cute thing if you create a system is there's a drop-down dialog box to pay for a petabyte of storage up front a month. And it's $25,000 a month, which isn't that bad. Over a year, it's $300,000, and as you add a second petabyte, it gets a bit bigger and bigger. So I think it starts off, a couple of petabytes isn't bad, but it soon gets expensive. But it's there. You can go. In fact, you can do that from a drop-down box. It's pretty cute. This connector is shipping in HD Insights. It's been back-ported to our stuff as well. I don't know about Cloudera. The code works. Where it's not so good at is in resilience. When things go wrong, you get an error message like error brackets null, which is generally the JSON parser failed. The last time I was dealing with a support call related to that, it's because the JSON parser was getting some HTML back saying, you don't have your proxy settings right. But, we have to debug that from a single error message, what's going on. So it's those little details of things happening in the field that catch you out that this one's going to have to work on. Let's upload that data from WASB to ORC, I think. So yeah, I'm going to copy it from WASB to ADL here as soon as I found my mouse. So this time, I've taken the awk data I loaded up to WASB. I've created a little data frame for that. Now I'm going to create one for the ADL, and I'm just going to do the upload from one to the other. So I'm migrating. This is all happening client-side. So I'm actually downloading from Azure Storage, then uploading remotely. If you are running inside Azure Microsoft Cloud itself, this is going to be nice and fast. Okay, as it is, it says it took 5 seconds, which is very fast, actually. So that's one of the things that I think, actually, WASB is a little bit faster than ADL. All right? But that's just, I think, you'd have to do your own real-world tests to come to a conclusion there. One thing to note is that WASB containers have a limit on size right now. I think it's half a petabyte or something like that. So ADL does not have those limits. Microsoft are talking about how there may be improvements to the Azure storage at some point soon, so we'll wait and see there. Me personally, I'm not taking any side in this which is better game. I just think that they're both interesting and leave it to that. Now, Amazon S3. Amazon, they are the market leader in the cloud thing. That means you have to work with them. If you want long-lived storage in Amazon S3 at an affordable price, that means Amazon S3 is where your data lives. Amazon S3, its architecture predates the notion of big data analytics. Okay, it's basically quite clear it was originally written for storage of things like, pictures of books on a large retail website, that kind of thing, where availability is fine. They don't mind eventual consistency if it takes a second or so for the updated pictures to get through. However, all the Hadoop analytics code expects things to be like a file system. We expect the file, when it's deleted, to go away. We expect the file, when it's newly updated, to be there. We do not expect, as you seek around a file, to accidentally get the old copy. And Amazon S3 doesn't always meet those guarantees. The biggest danger is that directory listings lag file creation. If you create a new file and you do a list, it may not be there immediately. If you delete a file and you do a list, it may still be there. That can break outputs, especially things like Spark. Hands up in the room, who is using Spark writing directly to S3? Hands up. Keep your hands up if you know that's a really dangerous thing that you shouldn't be doing. Okay, you've made an informed choice there. The problem is that when we commit work, we do a rename. And for S3, the way we do a rename is we cheat. We list everything in a directory tree, copy those files one by one, and delete. So it is not an atomic operation. It can fail halfway through in odd states. The time to rename is the time to copy. And if that listing gets a file that's not there, and then it tries to copy it, it gets into trouble. It goes, oh, this file's not here anymore. What do I do? And if you have a look through the Apache Jira on some of the Spark, you do see this is an intermittent problem, where the last task doing the work commits its work, does a rename, but then actually the Spark job committer tries to find those files to rename, and they're not there. So that's why it's historically been dangerous. The standard solution to this is you use DynamoDB as the database to give you consistency. First implemented by Netflix in their Semper tool. Amazon implemented it a couple of years back in their consistent EMRFS option. And it is now in the open source from S3 Guard. I will credit Chris over there in the corner for having done a large amount of this work. So if you have any questions about it, talk to him. Again, we use DynamoDB. You don't just get consistency. If you allocate enough I/O bandwidth from DynamoDB, you book up front, you can get faster performance as well. So for Hive queries and Spark queries, if you're working with a large data set, a big chunk of the preamble is listing the files, making decisions about how to partition it. That can take a lot of time on the object store. It's all serialized. It's slow. If you start using DynamoDB, you can actually get faster values. I'm not going to give you benchmarks, because that would be committing to something, but it can be actually faster. You do have to pay up front for that I/O, which is constant, irrespective of use. The key thing is it gives you that consistency you need. Without that, you cannot reliably do I/O back-to-back, where one operation is listing the other. If you've got a lag, say 10, 15 seconds, you might be all right, but certainly not instantaneously. So what we're doing is, how does it work? The answer is all the I/O, all the queries, the listings, they first go to DynamoDB, then they actually hit the object store. So the DynamoDB can actually act as a cache. Where, unless you say authoritative, it's a hint where we also do a listing of what's going on in the file system. So it remembers what's happening, it remembers the recently deleted files, and it deletes them from that big listing. But if there is an inconsistency between DynamoDB and what's happened in the object store, it's not too bad. There's a switch for authoritative mode where we'll actually say we will only do our listings against DynamoDB. It gives the real Hive performance numbers, but that is the bit that is most risky in terms of, do you trust this code? Okay, I'm going to be honest here. Right now, both us and Cloudera are qualifying it in the non-authoritative mode, just because it takes a level of commitment to say we're going to do this. How do you use it? You configure a property that says for a specific bucket, I want to use DynamoDB for my metadata. Then you just issue the command Hadoop cguard init, give the URL to the bucket or the specific URI of the DynamoDB and your I/O bandwidth, and then it just happens. So it creates it. I'm not going to give that command because it's already been edited, but I can just go bin Hadoop cguard. I did it there. It'll probably tell me off for actually having done it there. It creates a DynamoDB table. That table is now ready to play with. I can now go bucket info, and it will tell me what's going on with that bucket. This is just defaulting. It's taken the file name of the, that was an error, wasn't it?
You also have init there.
Oh, that's true. Thank you, Niels. Thank you for correcting me. There it goes. It says we are using it. We've got some values there. It says the magic committer's turned on, and it gives an endpoint and encryption, which is kind of handy. You can say, let's verify this thing's encrypted. So your I/O capacity determines your performance. If you create, like we've done here, we default to creating a bucket for a specific, so we create a DynamoDB table for a specific bucket, then whenever that bucket's not being used, you're paying for DynamoDB capacity that's actually being wasted. What we recommend you do instead is that if you have multiple buckets on the same store, and don't worry about all the users being able to list the contents of the other buckets, then you can have a single DynamoDB instance you share. So you basically say, I'm going to use a shared database for all this. You can allocate the I/O bandwidth for multiple buckets, but you can handle burst in one particular bucket and the other, and it evens out more. So that gives you consistency. It gives you the ability to chain work together nicely and see the answers. It also gives you that consistency we need to commit work by renaming. So you have to worry less about the problem. However, it still takes a long time to rename. The problem is that how we do that work, as I was showing, we do it in a temporary file. When a task has been completed, the task sends a message to whatever's in charge of the job itself and says, I'm ready to commit. The job manager then decides what to do. The Spark one first says, have I heard of this task at all? If it's got no idea who it is, it says, go away. Then it says, has this task already been completed? And says, it's been done, go away. Then, if it's work it's actually expecting, the first one that comes in, it will say, you go and commit. And any others that come in, if it's happening speculatively, it'll just say, hang on a moment. So they commit, and we do that commit by rename, which is nice, it's fast, atomic. The committer either returns saying, I've done, in which case everything's happy, or the committer stops returning in a certain time. Spark driver says, well, it's failed, this is not good, it tells another one to go. That's fine if you're using rename for commit, but if you're using something else, then, well, the way we're doing this rename file by file by file, it can actually fail partway through and you're in a mess at that point. This same failure mode happens actually if you're using the normal file output committer and saying commit algorithm 2. It's doing that same thing where it's copying, renaming some of the files to the final destination. And again, its failures aren't handled very well. They don't meet the expectations. The real issue, though, with the object stores are that it takes a long time. With S3, it takes a long time. Because we fake rename by delete, so by copy and then delete, it has to copy the data, which in S3 is about 6 to 10 megabytes a second. So you've got something that works really well in a small demo. It says, yep, I can work locally in a tiny data set. I'm happy. This is good. You take it to production. You think, why is it taking so long? It's suddenly taking hours at the end. And it's not even logging anything, because we don't bother telling you how long rename takes, because it's instantaneous. Why would you bother doing that? So it's the big bottleneck. The good news is we have a fix for that. It is a fix that I will actually credit, not Chris this time, but Ewan, Thomas, you in the room? No, those two, they work with me on it. And we've just embraced the object store itself. Rather than trying to pretend it's a file system, we accept the fact that object stores do things differently. And a key one is when you're writing an object store, you're doing a put operation where nothing is visible until you finally complete the write. So you can upload lots of data. It's not until you've finished your write that it becomes visible. The other cute thing, which is an insight from those two, is you can complete the write on a different host from where you started it. So you can have one process on one machine, upload all the data apart from the final post to say I'm done, and then you can hand off the information to the job driver to actually do the little operation to say, yes, go ahead. So that's the secret, really. Instead of writing to temp directories, we tell the workers to write straight to destination directory. We initiate a multi-part put, and you get some post ID. You give the final path. Then I can write multiple blocks in a sequence. This is exactly how we'd actually do large file writes today in the S3A committer. As you write, as we go along, we upload the data. Normally, when you close a file, that's it. It's done. It's immediately visible. Now we don't. We leave it hidden briefly. And so it's there, but it's not there. Amazon is still billing you, so don't think you can get away without paying. Okay, that doesn't happen. So you need to be able to list and delete this stuff, but it's not visible to other people. What we do then is each task remembers the information it needs to upload, which is the upload ID and the list of the blocks uploaded, and then we save that information to a file, which is then passed along to the job driver. Again, I have another task working in parallel. It can be writing to a different file in the same destination. We upload that stuff, and it's ready to go. You can also have two tasks speculative writing to the same destination file. It doesn't matter that there's any conflict. In the object store, whichever commits last wins. And because we're only actually going to be committing one of those bits of work in the job driver, then only one of them gets instantiated. So we get those files over, we list them, and now we commit the work in a single post, which is a very short file. It's just a lump of JSON listing the file ID and the list of blocks. It takes under a second per file, and it's parallelized, so we can commit a massive number of files in a few seconds. Not quite atomic, but it's close enough. Nobody really minds. Anyway, this is how it works. This is what Netflix have been using in production for a while, which is good. So they were using it. We took their code. If it doesn't work now, it is probably the fault of me or them. So ready to play with it. And you can use it from Hadoop MapReduce. We can use it from Spark as well. Apart from the small detail of getting things on the class path, the patch to commit these two binding classes is waiting for review in the Spark team. The committers themselves are in Hadoop 3.1. So all you need to do is hit the switch to say, I want to use a different commit protocol for most things. You have to have an extra switch for Parquet, because Spark is very Parquet aware. And then you choose, of the 3 different S3A committers we provide, which one you want, and the conflict mode. So let us do some work there. I'm going to take the data and write it to a file in Ireland, and it's coming from WASB again. I just don't want shell, I want Spark. So, clean up the old data. Now I do the write. So we've done it. It's hard to tell whether there's been a big long pause or not. The key point is that you're not seeing any information about the rename. We're just seeing some stuff saying we're doing some commits at the end. We give lots of information about how long it's taken to do all this work too. 0.4 seconds to do a lot of the work. So with this committer, you can use bulk I/O. Sorry, you can do large I/O direct to S3, and you do not take a performance hit in the job commit of how much data you've uploaded. So it is safe to use for large amounts of data. Now, an interesting question is, how do you know whether we use this committer or the old one? And the cute thing is that whenever you write jobs, whenever a job normally commits, it writes a little 0-byte success file to the file store to say, I'm done. And that's the official I've completed marker. Because we're using put, we don't need to write a 0-byte file. We can get away by writing a a large file. So we actually pump out a lump of JSON telling you what happened, various bits of statistics, and actually a list of all the files that's gone through. That was originally done for testing, but it's interesting. I want to do a lot more metrics, aggregation, and things like that there, so we can find out a lot more about what happened. So if you're using this committer, you look for the file type. If it's 0 bytes long, then actually your settings aren't lined up right. If it is non-zero, then all is well. Hands up who's excited about using this. Excellent. Grab it, play with it, send me emails if it doesn't work. I'll give you those two as email addresses as well. Anyway, so one thing right is that I talked about multiple committers here, okay? The first one is something called, the staging one came from Netflix. What it does, and it sounds a bit convoluted, but it does actually work, is you're running a Hadoop cluster in Amazon EC2 with local HDFS, and you need local temp file storage. What happens is the files are written locally to the local file system, just in a temp directory, until the task is committed, at which point, when the task is committed, it does the upload. And then it saves the information about how to commit what's been uploaded to a JSON file in HDFS, which is then propagated to the job driver using the normal Hadoop file system commit protocols. It seems a bit convoluted, but it does actually work. And what it does mean is, because HDFS is consistent, you do not actually need a consistent S3. So even though I'm talking about how CGuard gives you consistency in performance, you can get away with the staging committer without actually needing that feature, with the caveat that if you're running queries back-to-back, you will need that feature as things might not get found. Okay? So if you're doing one write and then you've got a delay, you can get away without it. So that's what the staging committer does. The partition committer from them is the same committer with a different conflict resolution mechanism. Normally, when you're doing a query and you say write to a destination, if there's any data there, the job immediately fails going, oh, there's data there. I'm going to give you a stack trace. So the normal workflow in the application is I write the data to somewhere, and when I'm finished, I rename it back into my big ongoing data set of everything that people have been watching over the last 5 years. What the partition committer does is it does its conflict resolution right at the final partitions. So I can send a query to say, I want to update. Imagine, Netflix, you really do have a data set of what people have watched, most popular films, over sorted by year, month, day, region. Then you can actually do new queries updating that, so we could update the April 18th data set in situ and not worry about the fact that there's any other existing bits of the table there. This query is only generating April the 18th data. If there's data there, you can basically say fail if it's there, but otherwise don't care. Or you can actually say delete it all, and I'm basically pretend that nothing happened. Don't worry about it. So you're not damaging any of the rest of the system. This is how Netflix have been using their committers to actually do large updates of very large data sets. They're not rerunning the whole query. They're just running incremental queries for the new day, the new hour, and they're just copying that into place using the partition committer. The final one, the magic one, is what Thomas and I and Ewan were doing before Netflix turned up, where we are actually not dependent on any local file system at all, and we are incrementally writing the data. What it's actually doing is it recognizes when you have a special path in the file system, _magic, that if I write to a path _magic, it says, OK, this is something special here. This path doesn't really exist. I'm actually going to write it to the parent directory. And under the magic directory, I'm just going to write the little JSON file telling me what to upload later. So the task commit just lists everything under _magic and copies it into place, and uses that to issue the post command to actually complete the puts, and that makes them appear. It's a bit of magic as you have paths in the file system that aren't there. That can catch things out that expect things to be there as soon as they've been written. And it does depend on that consistency that you get with CGuard. So Thomas and Ewing are playing with it because their S3 product is consistent, so they don't need the CGuard stuff. Right now, I'm qualifying this, and I'm basically saying I would start with a Netflix staging committer. That's the one they've been using the most. That's the one that seems a bit complicated, but it does actually work. They trust it. And try that one first. And I think, we don't want to lose data, so the magic one might be faster, but I think this one is initially safer till we've done more testing. So I gave you that quick demo there. That's good. We wrote the awk stuff, but actually, Spark has two interesting formats. There's Parquet as well. So let's do both as well. It's time I take the awk S3 stuff, write it as Parquet. I'm not doing the partition committer here. So again, it is reasonably fast. Took 4 seconds this time. Spark is very intimately involved with Parquet. That's good and bad. It's good. They get good performance. It's bad in that actually it took a bit more effort wiring this up because Spark has some expectations about how the Parquet committer works and what class it is and things like that. That's why we need a couple of binding classes in Spark, and you need to configure things. Again, you look for that success file, and that's how you know that everything actually got wired up correctly. And again, lump of JSON, snappy and Parquet. So that is essentially where we are with this stuff now. In Amazon S3, we've got the consistency, which is a feature where Apache S3A connectors caught up with what Amazon have been doing. With this new committer stuff, we're actually ahead of what Amazon are doing right now. They don't have this feature. I think it's faster. I think it's a really good thing to use. Now, another subject we need to talk about. Hands up who has CSV files. Yeah. Hands up who likes CSV files. You're faking it, okay. CSV files are kind of actually, the scary thing is they're one of the largest interchange formats on the planet. That's bad because it's not really a file as a format. It's more just a list of hints saying, oh, it's a text file with some unknown encoding that may use commas and spaces to separate stuff. And we'll argue about what metric format time is in. It is just a mess, okay? But it is out there. And the nice thing about it, or two things nice about it, is it's really easy to generate. You don't need any complicated libraries to generate a CSV file. You can use it in C with a printf statement. And pretty much everything has an adapter to handle it. They may not be able to handle the malformed stuff that the C program has generated, but at least they kind of expect it and do best effort. So Amazon have actually embraced the world of CSV as of 2 weeks ago with an announcement of something called S3 Select. Anyone heard of that yet? Was anyone at the Amazon conference where they talked about it? I was watching online. What S3 Select does is Amazon will let you issue SQL select statements as you download CSV files or one JSON kind of structure per row files in the file store itself. So rather than all the work we're doing so far, we're working with CSV formats and things like that there, everything is being done on the client. With this one, you can actually do some of the filtering of which rows to send back and which columns of that rows in S3 itself. Now, a question about why would you do that? And the key reason is that the bandwidth between Amazon S3 and EC2 is quite limited. And it's to do with the networking on the EC2 and some load balancing and things like that. So Amazon have a lot higher bandwidth between S3 and the bits of S3 itself than actually you come off S3. So if you can do the queries in S3 itself, you only get to download a subset of the data. So you only have to wait. Your bandwidth is only the network traffic you're using is only that filtered set. And if you're actually doing remote access where you are paying per megabyte from the data that's downloaded, you are only paying for the amount of data you've downloaded. So here then is a little select command I'm actually about to demonstrate where This is all proof of concept, but basically I can issue a command to say I want to select from the same Landsat CSV file I've been working before, saying I'm going to send a select statement here. So you say, I'm going to use a header. It's going to be compressed from this Landsat file. Just say select s.entityid from the object with a filter where cloud covers 0. It's using the header to work out the names of the columns. It's then just comparing the string values of this. It does actually support schemas, especially if you're working with JSON. But you can actually do, once you can use schemas, at which point you can start doing things when, say, cloud cover is less than 15. I'm not quite sure how well it handles timestamps, and that's a complication, is because, again, there is no standard representation of time. Anyway, let's issue a query for that. I'm going to take that, and this is going to be in the shell this time. I'm going to issue that command. So this is me issuing a select statement. There is no query engine running in the command line at all. All I'm doing is issuing a GET request, but this time with that select query coming back in, and I've only just got a fraction of what was actually there. Hands up who's impressed by that? Anyone? Yeah, those people that actually use CSV are going to be really excited now. Everyone else is like staring at it thinking, that's a nice idea, but what use is CSV? I'm not going to advocate CSV as a format of the future. Don't worry about that. They talk about maybe they'll support other file formats, I think would be the summary there. And we'll wait and see on that. I suspect it's easier to do filtering by rows and columns rather than more complicated structures where you have to seek around. I think it would be nice if they used Avro, because at least Avro has a real schema at the top, and because it handles numbers better, you can actually do timestamps better. So ask Amazon to support Avro, and then everyone can be happy. Now, there's another cute thing which it can do, which I'm not going to demonstrate because it's not working for me right now, bug in my code, is that you can actually, and this is purely my little proof of concept connector, is I can actually read in the data, like the full Landsat image, and then save it to ADL. So one of the big complexities and expenses in the cloud world is moving your data from one store to another is very expensive. You pay for all the bandwidth. I'm going to point out with S3 Select, you're only paying for that fraction of the data you're actually moving. So if you do have a large data set and you only want to get some of it, it's actually got a lot less expensive. Anyway, it's new from Amazon. It is stabilizing still. What I've just shown you there is purely a proof of concept that was put together for the launch last week. It's only on the command line. For this thing to actually be used, here is what needs to be done. We need to upgrade the Amazon SDK everywhere, which is always trouble. We need to provide a proper API for Hive and Spark to actually use. Right now, I've added a little backdoor API call into the S3 file system because I know it's there. So this client goes, OK, I get the file system, I cast it to S3A, I issue a select. That does not work for the other stores that don't want to know this thing. We've been discussing for a long time to have more of a builder model for opening files in the Hadoop file system APIs. That's what we'd have to do to implement this. Say, right, we'll make a more generic API. Then you can issue select statements this way without caring what the file system is. That's nice, as it also allows vendors of other object stores to go the same way. And then once we've done all this stuff, we can actually start looking at integration with Hive and Spark. My colleague Jesus, who is around somewhere on the site, he's actually done the initial proof of concept of integrating with Hive, by the way. What he did there was effectively modify bits of the ORC client to say you work with CSV and now support predicate pushdown. Nobody's CSV reader right now has ever had the idea of predicate pushdown before, so it is complete rewrite time for all this stuff. It does mean, if I look at what it would take to get it into Spark, we could write it as a completely separate module. There's no point right now trying to even get it into Spark proper. Finally, Google Cloud Storage. It's there. It works. As more people use GCS, primarily for TensorFlow apps and the like, it's getting used more. I haven't seen any support calls for it, so that has me happy. That's pretty much it. End of talk, really. So last bit of homework is I'm going to have to fix this CP for this world. If you have any questions about this CP, fix it yourself right now. Sorry, I ended up getting field requests. We're dealing with scale problems, the fact that there's still renames going on there, and just better incremental writes across object stores rather than relying on checksums being consistent everywhere. So this CP is time for refresh. And that is the end of my talk. I'll be around at lunchtime if people want to see questions and demos. Yes?
One of the suggested solutions you find on Google when you search for the slow rename in S3 is using the file output committer 2 in Spark.
Okay.
Do you know how it works?
Yeah.
Whether it should be used?
The answer is I know how it works and no, it shouldn't. Okay, just no. So the question there is that I was complaining about the committer, the file output committer, the classic one doing big slow renames. And if you set Hadoop map Spark Hadoop map produce file output committer dot algorithm equals 2, things get a bit faster. What's happening is the rename is still taking place. Now they're taking place when the task is committed rather than when the job. So the renames are still happening. It's happening slightly earlier. However, not only is your task committer going wrong, but if your task fails partway through that commit, your system is in an unknown state. So basically, you've lost that resilience to task commit failure. It's still doing a rename, and you've lost one of the core aspects of task commits, which is they should commit atomically. And so it's kind of dangerous. Really, if you look at the code, the Hadoop MapReduce v2 commit algorithm is not a real commit algorithm. It's more kind of a best effort. Question at the back?
Is there a write-up of all this excellent information? Because I want to share it with my colleagues, but if I tell them, watch this 40-minute video, they say like, I don't know. So is there
I don't think we're being videoed, actually.
okay.
For the slides will go up. For the committer stuff, there is actually, I've got a draft of a full paper on it. I think it's called Towards a Zero Rename Committer. Okay. What's the title? A zero rename committer is the name of that. The LaTeX and PDFs are up on GitHub. That's kind of the academic class paper on it. The other stuff, the slides will be up. Okay, so that's what you get. The committer stuff is kind of scary. Not just in the complexity, but is one of the scariest pieces of code I've ever seen. It's the only piece of code I've ever seen in production that uses co-recursion. And it's not like an elegant computer science co-recursion. It's more like an ugly hack someone put in to get this thing working without people noticing. And the only way to understand it is actually basically setting breakpoints and stepping through, taking notes with a piece of paper. It's why when I added a new committer, I didn't subclass that code. We stuck something in on the side, the notion of a path output committer. And it's made integration slightly harder, but it's just, it would have been too easy to break that code, and we'd have just made maintenance even worse. All right, question?
Yeah. If I want to run a Spark job in one cluster, for instance, ephemeral cluster, I still will have to have Hadoop installed to use SD card?
Okay, question is running Spark in an ephemeral cluster. Do you need a HDFS cluster as well? Right, if you're running HDFS, you get significantly better performance. You get the locality. You don't need it if you're running purely with S3, which is what this delivers. However, you will find things slower just because the connection between EC2 and S3 is slower. Netflix, they actually treat HDFS purely as a temp file system. So yes, you do it, you set it up, but it's purely for temporary storage. And so that's because Netflix have lots and lots of Hadoop clusters. They create them based on the current workflow. They have persistent ones, they have transient ones, they have runs that are just massive. And I think they use a tool called Asgard. They direct queries to whichever of those clusters has capacity for compute, and they use S3 as this store of record across all their data. So they use S3 as both the source and destination of all their work. If you're not into massive multi-cluster workloads, which most people aren't, you can just chain things together in HDFS, And for intermediate jobs where you don't want it persisted for other applications, that gives you really good data locality and performance. So your next query, you can do the work right next to where the data is, and it's a lot faster because you're not using any network traffic. Does that answer your question?
Yeah, it basically means no, but it isn't.
It means it depends. Okay, I'm basically saying things are faster if you use HDFS right now, would be the answer, and things will stay that fast because S3 has network bandwidth limitations between you and your VMs, and it depends how much you pay for your VMs, how much network bandwidth you get, doesn't it? Right, I think that's the end of our questions, so everyone go and have lunch, and I'll be around if you want to find me at the HortonWorks booth to ask harder questions.